Hello, everyone, and thank you for joining us. My name is Wyatt Pena, and I'm the Vice President of Operations here at Ridgetop Group. Today, I'm excited to share the results of a collaboration project with the University of Arizona and the College of Engineering, where we sponsored a senior capstone program to adapt one of our legacy PHM technologies, Sentinel Power, for a new and timely application, diagnosing failure modes in HVAC capacitors. As many of us living in desert climates know, air conditioning isn't just important, it's critical. This project demonstrates how real-time health monitoring and predictive diagnostics can protect essential infrastructure using a proven PHM framework. For our agenda, here's a quick look at what we'll cover today. A brief overview of Ridgetop and our background in reliability engineering, the challenge and opportunity that led us to explore PHM for HVAC applications, an overview on prognostics and health management, what it is, how it works, and why it matters, a detailed introduction to Sentinel Power, some key highlights from our collaboration with the University of Arizona and the prototype they developed, our future technology roadmap, including an upcoming pilot deployment project we have planned for this summer, and finally, a brief recap followed by a Q&A session. Let's start out with a quick overview of our company. So on this slide, we can see that we were founded in the year 2000 and are headquartered out in Tucson, Arizona. Ridgetop specializes in the design and development of hardware, firmware, and software solutions for condition-based maintenance, or CBM, and prognostics and health management, or PHM, and reliability engineering applications. Our mission is to improve safety, efficiency, and operational performance while reducing maintenance and sustainment costs for our customers. We offer a full range of engineering design services, including custom circuitry for harsh environments, embedded systems development, and an advanced diagnostic software for aerospace, defense, transportation, energy, and industrial markets. We are also proud to be an AS9100D and ISO 9001 certified company, ensuring that our quality management system meets the highest standards in regulated industries. With over 2 decades of experience, Ridgetop continues to set the standard in prognostics and health management, and we are now applying this expertise to new domains like HVAC applications, where equipment uptime and predictive maintenance are becoming industry essentials. To kick off this webinar, let's take a look at real and persistent challenges in the HVAC industry, especially for those of us living in desert climates like the American Southwest, where HVAC failures are a common and costly disruption for homes and businesses alike. On this slide, we see a split view diagram of a typical scenario. On the left, we have an HVAC unit that fails suddenly during peak summer heat caused by a degraded start capacitor. These components tend to fail silently over time, offering little warning before the system shuts down entirely. In places like Arizona, where temperatures often exceed 110 degrees Fahrenheit in the summer, these failures aren't just inconvenient, they pose serious health and safety risks. Beyond safety concerns, these failures can also have major financial impacts, particularly for businesses that rely on regulated temperature control for operations such as data centers, manufacturing centers, healthcare facilities, or commercial real estate. In these cases, an unexpected HVAC failure can disrupt workflows, trigger compliance issues, or drive up emergency repair costs. This problem is made worse by the fact that most HVAC systems today still rely on reactive maintenance or basic built-in self-tests. These methods might detect a problem after it happens, but they rarely catch early warning signs like subtle changes in resonant frequency, ripple voltage, or current consumption that indicate a component is starting to degrade. Now, if we take a look at the right side of that diagram, this represents the future of critical asset monitoring across many industries. Through smart sensors, IoT connectivity, and cloud-based analytics platforms, we can continuously monitor systems' health in real time and even build out digital twins of physical systems for diagnostics and simulation. If you're familiar with Industry 4.0, you've likely seen how technologies like IoT or the Internet of Things, cloud analytics, and real-time sensing are transforming the way we manage and maintain critical infrastructure. At Ridgetop, we spent over 2 decades developing reliability engineering solutions for demanding sectors like aerospace, transportation, and energy. Now we're applying those same proven principles to HVAC systems. In today's webinar, we'll walk through how we have collaborated with the University of Arizona to adapt our patented PHM techniques, specifically the ring down approach within the Sentinel Power, to tracking known failure mode with capacitor degradation in HVAC systems. The resulting sensor data is then processed through our adaptive remaining useful life estimator A-rule that calculates state of health and remaining useful life and helps inform proactive maintenance decisions. Instead of waiting for capacitors to fail, this predictive approach enables early alerts and scheduled service, helping prevent costly downtime and unplanned disruptions. This approach has already been validated in aerospace, automotive, and industrial power systems, and we are now bringing that same level of intelligence and reliability to the HVAC domain. On this slide, we'll explore how maintenance practices have evolved across industries, not just for HVAC systems, but several others as well. And there is a clear transition from reactive maintenance to preventative maintenance, and then to condition-based maintenance, and now towards predictive maintenance and PHM capabilities. For reactive maintenance, in the early days, most systems followed a run-to-failure model, where equipment was only fixed after it broke. While simple, this approach often led to high repair costs, unexpected downtime, and even safety risk. It is also the most common maintenance method used in HVAC systems today. Next came preventative or interval-based maintenance, which is where a technician or maintenance personnel come out, perform maintenance based at a fixed interval, regardless of the actual condition of the system. While this is a step up from reactive maintenance, it has often resulted in over-maintenance or inefficiency and servicing healthy systems while missing fast-degrading components. Next, we have condition-based maintenance, where the rise of digital sensors and diagnostic capabilities have marked a turning point. With condition-based maintenance, or CBM, maintenance can be triggered based on real-time health indicators, such as temperature, vibration, or electrical behavior data streams, which create a data-driven approach and has laid the foundation for modern systems that make maintenance based on actual evidence of degradation. And finally, we have predictive maintenance and PHM strategies, where today more and more industries are finally embracing this type of approach. At Ridgetop, we've been developing PHM solutions since the early 2000s, and we have seen adoption vary by industry and asset criticality. In the past, technology and cost barriers have often limited PHM deployment, but thanks to advances in IoT connectivity, cloud computing, and embedded processing, these solutions are now far more practical and cost-effective for new markets and applications. This is especially promising for the HVAC industry and other industrial IoT sectors. Predictive PHM solutions don't just monitor current system health. They apply advanced algorithms like our A-roll engine to predict future failures and estimate remaining useful life. When combined with IoT platforms, these tools can now be scaled across several different industries. So why does this matter? According to industry benchmarks, companies that adopt predictive maintenance and PHM methodologies have been able to achieve key improvements such as 30 to 40% lower maintenance costs, 70% improvement in equipment uptime, and up to 50% longer asset lifespan. For HVAC systems in particular, this translates to fewer emergency repairs, better comfort control, and lower lifetime costs, especially when paired with IoT-enabled solutions like Sentinel Power, which offer a centralized cloud-based monitoring platform. So what exactly is PHM and how can it be applied? PHM, or Prognostics in Health Management, is a structured methodology that enables critical systems like HVAC units to continuously monitor their condition, to detect emerging faults, and forecast future failures before they happen. Rather than focusing on just one function, PHM works through an interconnected set of frameworks, each providing a critical layer of insight and action. Together, these frameworks help organizations move from reactive or time-based maintenance to a more intelligent and predictive strategy. Here's a high-level breakdown of the key components as shown in the diagram in the lower right. At the core, we have a control and data flow framework, which acquires real-time sensor data such as voltage, current, vibration, temperature, etc., from a sensor framework or sensor array. Next, we have a feature extraction framework, which processes this data to isolate meaningful condition indicators or early failure signatures. Such feature data can then be utilized and processed with a prediction framework, where advanced models like A-roll can determine state of health, remaining useful life, and prognostic horizon, allowing operators to anticipate failures well before they occur. We also have a fault management framework and performance validation framework, where the fault management framework helps support risk-based decision-making for maintenance teams to prioritize actions and allocate resources effectively. For the performance validation framework, this is utilized to continuously assess system performance, reducing false positives, and refining the accuracy of predictions over time. When all of these frameworks are integrated into a full system-level solution, this is what makes PHM so impactful, especially for critical assets like HVAC systems. And these are the types of solutions Ridgetop has specialized in the development for our customers. Instead of servicing equipment based on a fixed schedule or waiting for a breakdown, PHM uses live data and predictive analytics to detect early stage degradation and guide proactive interventions. While pioneered in high reliability sectors like aerospace and defense, PHM is now becoming essential in commercial and industrial domains like HVAC, where uptime, energy efficiency, and predictive control are fastly becoming the new operational standard. On this slide, we can see a more systematic approach on how to organize each of these frameworks, where the IEEE 1856-2017 standard defines a reference model composed of 5 core PHM operational processes with sensing, acquiring, analyzing, advising, and acting, which is further broken down into 8 key functional blocks. These blocks work together in a PHM system to enable effective monitoring, diagnostics, and decision-making. In this diagram, we can see the 8 functional blocks starting from the bottom with sensors, data acquisition, and data manipulation, which could be part of an existing asset or may need to be added as an aftermarket add-on to improve asset reliability. Next, we have state detection, health assessment, and prognostic assessment, which identifies whether the system is operating normally or exhibiting abnormal behavior, evaluates the current degradation levels, and highlights which components require attention, and also forecasts future performance with predictive analytics that compute state of health and remaining useful life. Finally, near the top, we have the advisory generation and health management functional blocks that help provide actionable notifications and recommendations, such as generating a text, SMS, or email alert that would help an operator schedule maintenance or do that with an automated process if it is a closed loop system. And then that maintenance or health management action can be executed, which is what helps the system get restored back to an operational or healthy state. Following this proven standard, your PHM implementation becomes modular, interoperable, and scalable, ensuring it can easily integrate across multi-level systems or systems of systems, and also evolve over time. In industries where safety and reliability are top priorities, such as aerospace and transportation, it is considered a best practice to incorporate each of these functional blocks into the system level design before the development and deployment. We are also proud that Ridgetop team members have had the privilege of working with the IEEE Reliability Society, contributing to the original IEEE 1856-2017 standard, and also helping shape the forthcoming update with 1856.1. This new standard focuses on best practices and lessons learned for designing, developing, and deploying a complete PHM system level solution. On this slide, we can see a visual representation of how PHM processes can be deployed across the broader HVAC ecosystem. In this example, an HVAC system is continuously sending operational and health data to an integrated diagnostics and prognostic software platform. This platform enables maintenance and reliability engineers to monitor equipment status in real time, assess state of health and remaining useful life, and even identify potential design improvements over time. Based on the insights generated, the system can automatically trigger condition-based maintenance or predictive maintenance actions, such as ordering replacement parts, minimizing on-hand inventory, scheduling service windows, and ultimately executing the repair or replacement using a line replaceable unit. This closed-loop process ensures smarter, faster, and more cost-effective maintenance decisions and strategies that can reduce downtime and optimize asset performance across facilities. Now that we covered what PHM is and why it matters, let's shift our focus to Sentinel Power and explore its origin and capabilities and relevance to HVAC systems. So Sentinel Power is an advanced PHM solution originally developed by Ridgetop to address failures in aerospace-grade power supplies. Over time, it's been adapted for use in a variety of mission-critical applications, including backup UPS platforms, PC power supplies, and most recently, HVAC capacitors. Thanks to a successful collaboration with the University of Arizona, which we'll cover here shortly. But first, let's take a look at what makes Sentinel Power a unique PHM solution. So Sentinel Power integrates our patented power signature monitoring sensor, smart probe sensors, advanced prognostic algorithms like A-roll, and a graphical user interface known as Sentinel Power View. Together, this system monitors power supply components for a range of degradation mechanisms, including the loss of filtering capacitance, the loss of gain and feedback loops, the loss of phase margin, loss of filtering inductance, and even the loss of effective parallel resistance. These failure modes often stem from electrical stress, aging, or thermal degradation, making them ideal targets for a PHM solution. To capture these fault signatures, Sentinel Power uses 2 key sensing technologies, including the Smart Probe 4000, which detects shifts in resonant frequency, and the Smart Probe VA, which analyzes ripple voltage and harmonic distortion. Once collected, the data is processed by Ridgetop's prognostic reasoner A-roll, which outputs key health metrics such as state of health, remaining useful life, and the prognostic horizon, or time to failure. This architecture enables early fault detection, root cause isolation, and actionable predictions that support smarter maintenance decisions across industries. Here we have a system level view of Sentinel Power showing the hardware and software components working together. On the left, we can see the sample mode response technique or smart probe sensor physically connected to a power supply and a computer or laptop that is running Sentinel Power View, which is a software application and serves as the primary GUI for collecting and analyzing sensor data. We originally developed this particular setup to support a highly accelerated life test where we programmatically degraded the filtering capacitance in a modified PC power supply system. The smart probe captured the resulting changes in ring down frequency, which is a key type of feature data that reflects the system's dynamic behavior as it degrades. This architecture has since evolved, forming the foundation for a variety of customer-specific implementations, ranging from custom hardware and firmware to full software stacks with API integrations for advanced diagnostics. This slide offers a quick visual for the highly accelerated life test setup that powered our early demonstrations. This configuration is now available as part of our R&D development kits, which are ideal for pilot studies or proof of concept evaluations. These kits include everything needed to replicate the ring down test and methodology, including the smart probe sensors, the programmable degradation modules, and a licensed version of Sentinel Power View and April. For research teams, OEMs, or reliability labs looking to validate prognostic frameworks in-house, this setup provides a compact and effective entry point into PHM-enabled diagnostics and prognostics. On this slide, we have a quick video of the HALT demonstration in action. So as this test runs, we are programmatically removing the filtering capacitance from the power supply under test, and we'll notice a corresponding shift in the ring down frequency, which is extracted by the smart probe sensor in real time. This feature data is streamlined directly into the A-Rule predictive analytics engine, or is processed continuously to track the power supply degradation curve. On the bottom plot, we'll see the state of health gradually decrease until it eventually reaches 0%, indicating functional failure. This is a real-time convergence between physical degradation and predictive modeling, and it is what makes Sentinel Power such a compelling tool for both lab diagnostics and embedded applications. It is also important to note that this monitoring change in the ring down frequency was the baseline approach for looking at the HVAC capacitor failure mode, which we outlined for the senior Capstone project with the University of Arizona. This slide provides an overview of that particular collaboration project where a multidisciplinary senior Capstone team successfully adapted the Sentinel Power system to monitor a portable HVAC start capacitor. As a quick summary, they built a full prototype using a commercial IoT board implementing both ring down and voltage decay sensing techniques, where these signals are processed using our A-Roll engine to track capacitor degradation in real time. And the students also developed a custom GUI that displayed health metrics like state of health and remaining useful life. The results we see on the right include the system block diagram and the captured signal data from their initial prototype. But the following video provides a more comprehensive recap of their year-long project.
Hello, and welcome to our video presentation for Project 24502, Wireless Sample Mode Response Technique for Power Supplies and HVAC Systems. This project was sponsored by Ridgetop Group, a company specialized in condition-based maintenance and prognostic health management. Hi, I'm Amy Nikaido. I'm the team lead, and I'm an engineering management major.
Hi, I'm Nicholas Rowland. I'm the procurement lead, and I'm an electrical and computer engineering major.
Hi, I'm Luis Hernandez. I'm electrical and computer engineering major.
Hi, I'm Mohammed Rakhayes. I'm an electrical and computer engineering.
Hi, I'm Qasir Mustafa. I'm an electrical and computer engineering major.
Air conditioning units utilize capacitors in order to initiate the rotation of the motors and to keep the motors running. The start capacitor fails the most often, which is not only inconvenient, but also dangerous in areas like Arizona, where the outside temperature often exceeds 100 degrees Fahrenheit during the day in the summer. Our project goal is to avert these inconvenient failures and reduce downtime of AC systems by monitoring the start capacitor and estimating its remaining useful life. By doing this, the start capacitor can be replaced before failure. Our goals were approached by developing three main components: a wireless sensor that can safely collect data from the capacitor, an application programming interface, or API, that can process the collected data, and a graphical user interface, or GUI, that can display the collected data along with an estimate of the remaining useful life. In addition to this, our system needs to be low cost and have a small size in order to be compatible with many configurations of AC units.
To tackle the first requirement, the Arduino Maker Wi-Fi 1010 microcontroller was chosen because it fulfills many requirements of our project. This includes Wi-Fi connectivity, backup power capabilities, and backup storage in the form of an SD card. By utilizing this microcontroller, the functionality of the sensor is done entirely through the Arduino's firmware, which is written in C. The Arduino is able to connect to a user's Wi-Fi network and send data wirelessly to our API and GUI. This makes data collection and monitoring easy for the user, who is able to manage all of this through a computer.
The main requirements for the sensor were that it should be able to connect to Wi-Fi to send data wirelessly and take measurements while the AC capacitor remains connected to the HVAC system. Tackling the second requirement of the sensor required developing a circuit that could connect to the capacitor and the Arduino, handle the typical voltages used in an HVAC system, and simultaneously keep the Arduino isolated from the HVAC voltages. The Arduino that was chosen for the project can only tolerate up to 3.3 volts, so it was especially important to keep the Arduino isolated and make sure that the circuit can handle the high voltages. To achieve these goals, the circuit and final PCB was designed around the use of relays. By utilizing appropriately rated relays and components, the Arduino and the circuit are able to safely interact with the AC capacitor without the risk of damage. Relays are used to disconnect the capacitor when the Arduino receives a measurement command from the user. Relays are then used again to connect the capacitor to a high wattage bleed resistor on board the PCB to allow any remaining voltage to discharge.
The two types of measurements that can be taken are a voltage decay measurement and a ring down measurement. The voltage decay measurement is done by connecting the AC capacitor to a high ohm resistor on board the PCB via relays, and then having the Arduino pulse in 3.3 volts. The discharging voltage across the resistor is read by the Arduino, which stores the time versus voltage data in a .csv file.
The ring down measurement is similar, but instead utilizes an inductor in place of a resistor to create an LC circuit. This circuit connects to the capacitor to an onboard inductor, pulses in 3.3 volts, and then stores the time versus voltage readings in a .csv file.
The API was required to transfer data to the server in a .csv format and to handle all requests wirelessly via HTTP protocol. The ability to transfer data was handled by writing a Python application. This Python app grabs data from the Arduino and sends them to the server hosted on the Odyssey Mini PC. From the server, the API can send the data to ReshTop's the Adaptive Remaining Useful Life Estimator or AROL software, which is able to process the data and give a remaining useful life estimate. The processed data can then be sent from the server to our GUI to be displayed.
The GUI was designed to be user-friendly, with the main goal being to display processed data, control the sensor, and connect with the AROL. This included sending commands to start a new reading. The GUI was built with an HTML front end for an easy-to-use interface and a back end using JavaScript and Python for smooth functionality. The API manages how the GUI connects with the AROL, using the HTTP protocol to handle requests efficiently.
For many of us on the team, this was our first time working on an interdisciplinary engineering project and dealing with the difficulties that would be present in such projects. We learned how to work together as a team, effectively manage our project in time, and approach design problems. We also learned how to apply our electrical and computer engineering knowledge in many different applications, from software development to handling and taking precautions when working with high voltage components. In conclusion, we have developed a comprehensive sensor system that measures voltage decay and ring down data, supports wireless transmission, and includes backup power and memory. Data is transmitted via an API to the server where it is pre-processed and stored. Our GUI estimates the capacitor's remaining useful life using AROL, displays raw and processed data, and allows users to manage the sensor's data collection settings. We would like to thank our sponsor, Ridgetop Group, our mentor, Professor Roger Elkins, the College of Engineering, and our family and friends for their continued support throughout our project.
As we kind of near the end of our webinar today, I wanted to take a moment to thank the University of Arizona and all of the team members on the Senior Capstone project for their outstanding work on the video. Again, as we just saw, summarizes their contributions, and their efforts have also laid a strong foundation for what we're doing now and what's coming next. So they also earned multiple awards during the design day, and it was an honor to be able to collaborate with such a talented team. Since receiving their final deliverables, our engineering team here at Ridgetop has been reviewing and building upon their work to design and test a new hardware revision that also integrates with our new software platform. So this version will serve as a pre-manufacturing prototype and will be part of our field test on the Ridgetop building, which includes more than 20 rooftop HVAC units. So our goal is to capture multiple real-world failure modes under live operating conditions on much higher voltage systems than the portable HVAC unit we did with the Senior Capstone team. So in parallel, we are also partnering with local HVAC service providers to help deploy the system in larger commercial real estate properties. And these pilot programs will help us evaluate the technology's performance and scalability across different environments. Together, these next steps bring us closer to delivering a smart and deployable diagnostic solution for HVAC systems, driven by a set of proven PHM capabilities. To summarize our webinar today, we can conclude that HVAC capacitor failures are a serious and preventable issue, especially in high-demand environments like ours. By applying proven PHM principles and methodologies, we can move beyond reactive service models and begin to make decisions in real time based on physical evidence of degradation. During our webinar, we also covered the fundamentals of Sentinel Power, and through our collaboration with the University of Arizona and the Senior Capstone team, we have validated both the technical approach and the potential impact of this technology in a practical setting. Our next step is to scale this technology with a larger field test across the 20 plus rooftop units here at Ridgetop and the local pilot projects with the HVAC companies. And once complete, our goal is to be able to deliver each of these proven solutions that will help improve HVAC reliability and reduce downtime and lower equipment lifecycle costs. So thank you again for participating in today's webinar, and we welcome any feedback, questions, or ideas you may have. Feel free to reach out to us through our website or through email.